Okay, Labrit, good morning. Well, it's a really nice occasion today. It's not so frequently Prof is coming to Riga, but now he is going to present us very good topic about general issues and science together. You're welcome. But you want to say something, some welcome, because 15 minutes is just to say something very good about our presenter.
Yes, so I will tell a few words about Lorenzo Pavesi. So how we met, we with Inga Britze went to winter school in Trento, and it was good to learn from good scientists. And during this winter school, we also had this skiing, and so it was a very pleasant time, and we made good contacts. And when we applied for a new project, so for this RHR project, we need somebody in advisory board, some recognized researchers, and so I invited also Lorenzo Pavesi to be there, and so he agreed. So we were very happy, and so we have collaborated and interacted with him for several years. And he arrived here a few years ago to understand the situation here, and then after that we searched for our RHR. And then we collaborated remotely, and 1 month ago, Jan Salnes with his team visited Lorenzo in Trento, and now we invited Lorenzo Pavesi. We have our conference, which will be tomorrow and on Friday. And before that, we thought that it's good to have additional seminar about quantum sciences. In Latvia, so in Europe, there is a quantum flagship to stimulate quantum technologies and quantum simulations. And then each country puts some additional efforts to proceed with this topic. And in Latvia, we also started projects called the Latvian Quantum Initiative. And there they combined about 7 groups from various institutions. And they also wanted to develop this topic. And for us, it would be useful to learn how everything happens in other countries, for example, in Italy. And Lorenzo Pavesi is the director of one of such project or initiative that they combine several research institutes. They made quantum initiative for Trento, or maybe it's another word for this is, and then they made PhD program, made research, collaborated with industry. And so I planned this seminar that we can learn how it's happening in Trento, how they organize this, how they organize interaction among researchers, how they select topics, how they distribute funding, how they collaborate with industry, so that we can learn and to get this exchange of ideas. And for the seminar, also invited those who are in this Latvian Quantum Initiative, but this meeting overlaps with this next conference, which is the Deep Tech Atelier, which will be tomorrow and Friday. And today they have some company visits, so they couldn't participate, but they said they are interested in this seminar and to learn from Lorenzo Pavesi, and so they will be interested to hear this seminar. So it will be video recorded and will be available on YouTube. And so this seminar is not so much specifically about research; it's more about organization thing. And so we would like to hear your situation, what you achieved, and what we can learn from you. Thank you.
Thank you very much. Can you switch
yes,
the presentation, please?
This is the first. Oh, no, not the first.
Yeah, this is the first.
Okay.
Okay, so thank you very much. Thank you for the invitation. I'm really proud to be here, especially because you are doing a great science. And so I really enjoy to collaborate with you. And each time I came here, for me, is a motivation to continue even in my work. So, and today, so it's quite a strange and a different seminar with respect to what we are typically used to here, because this is more a seminar that is about an initiative that we promoted a few years ago in Trento. And I want just to make with you, to share with you the way we proceed. And I will be very happy to discuss and get also your insights. So maybe you can also help us to improve this initiative. And then maybe we can also set a formal collaboration between the different initiatives, for example, because this is something that we are doing. Anyway, so the first thing is about the logo. So in order to make this, okay.
Move to the right. Touch on screen and then move to the
Okay, so in order to select this logo, so we made a competition by all the students at the university, and the requirement for participating to this competition was that the logo had to be proposed by at least 2 people coming, one from hard science and the other one from soft sciences like art or humanities or. And then the student proposed the logo, and this one was the one selected. So the people who got the selection so got also an award. And so what you see here is the fact that here we have the name of the initiative, that is QATN, meaning Quantum at Trento. And then you have those symbols here. So the blue stripes is something that remember you the fact that quantum physics is about wave function, is about photons, is about single atoms. And then you have the 2 stuff there. Can you guess what those triangles are?
mountains.
Yeah, the answer is mountains, because we are in a small town between the mountains. So these are the Palle di San Martino that are very nearby where we are. And this is the situation this Sunday. This, by the way, is me. And so the outline of my talk is the following. So I will start to introduce the initiative. And then I will try to say, to motivate the reason why we did this initiative and who are the founders, which is the network that is involved. Why do we have promote this initiative in Trentino, that is our small region, and what are we doing? So both with respect to research, education, innovation, and then since Igars asked me, so I also show you how do we work with companies. And finally, I will make a couple of examples about the kind of science that we are promoting. So what is QATN? So QATN is a formal joint laboratory between the research center in Trentino, that is the University of Trento, and the Bruno Kessler Foundation. I will tell more about those. And the 2 national institutes. One is INFN, that is the Institute for Nuclear Physics, that is a large institute in Italy, is the one that for Italy runs CERN, is the one that for Italy runs ESA, is the one that for Italy runs all the international collaboration in high energy physics. And then CNR. CNR is the National Research Council, is a huge council that is spread all over Italy. And what this makes this kind of laboratory interesting is the fact that we have a local as well as national collaboration. And the topic of the collaboration is quantum science and technologies. And the idea is to try to leverage on the resources by all the different institutions and on the state-of-the-art infrastructure coming from all the different partners in order to do a good research in local, in Trentino, but also try to get an European outlook, so to emerge at the European level. So the history is the following. So we start in 2018 with a first agreement between university and the Bruno Kessler Foundation. So we got some funds by the a bank foundation in Trento and by the local government. And then after 3 years, so we decided to move a step up and to formally form this joint lab. And so this is coming from an agreement between the 2 research institutes in Trento. Then few months later, INFN formally joins the agreement. So the president of INFN joined the agreement, and then the president of CNR joins the agreement. And then in the hereafter, so we start to get agreement both with similar Italian initiatives like the one that is run in Trieste or the one that is run in Padua, to a town nearby in the north of Italy, as well as with formally signed agreement with companies. And at the moment we have formal agreement with Atos, that is a large multinational company that is working in computer science, and then with AWS, that is Amazon Web Service, that probably you know. So why, the motivation why we try to promote this in Trentino? So the reason is that we had a very strong commitment by the local government that share with the university the fact that the way to promote innovation at the local level is to promote education and research. So therefore, our government is putting a lot of effort in trying to fulfill this positive loop between the education, research, and innovation, in order to have this as a promoter of welfare at the local level. And so the local government is supporting local foundation where a lot of research is done. So one on high tech, this is the Bruno Kessler Foundation, as well as one on agriculture, that is the Edmund Mack Foundation. So the environment was positive with respect to investment in research. And then at the local level, so in Trento, we have two big institutions. One is the University of Trento, that despite is among Italy one of the youngest university, is quite well ranked in Italy as well as in Europe. Just to give you a few numbers, so there is the research, the national research evaluation that each few years is performed at the Italian level, and so we rank it first. And then, for example, so we are running in this moment something like 20 ERC-funded projects. I personally am running 2 of them. Then we have many European projects. We do have also startups that are created by university research. So the university is quite small, Italian-wise, so we have only 700 professors and 70,000 students. But despite this, so as I said before, so the university is quite active. And what we say is that we are a research-intensive university. On the other hand, at the very same place where we are, so there is this Bruno Kessler Foundation, that is the instrument by which the local government try to promote advanced high-tech research in Trentino on 2 different main topics. One is artificial intelligence, and the second one is in microelectronics and sensors. And for this reason, so in this Bruno Kessler Foundation, so you have something like 400 research that are working exclusively on research. And what is very important for us, so they have a large technological facilities where devices can be produced and packages. So the Bruno Kessler Foundation is also doing a very good results in terms of scientific excellence, as well as they are running a large number of European projects as well as local projects. So those were the 2 main partners at the local level. And what is specific of this initiative is the fact that this is a transdisciplinary, interdisciplinary initiative. What I mean is the fact that since we are working on quantum science and technology, we are not only limited to physics. And so what we are really trying to do is to get involved in this initiative, and we have in the involvement of this initiative also of other departments, like the Department of Mathematics, the Department of Industrial Engineering, Information Engineering, Computer Science, Civil, Environmental, and Mechanical Engineering. So I should say that all the hard science and hard technology department of the university are joined the initiative. Then we have the Bruno Kessler Foundation that, as I was saying before, so they have many different centers. So the centers of sensors and devices where all the technological facilities are in, and then the other centers on the application of artificial intelligence to different sectors, for example, to the medical sector or to the manufacturing sector. Then in the initiative, so we have the INFN, that is the National Institute of Nuclear Physics, with the local center as well as with the national sections and laboratories, and finally the CNR. And the CNR is joined the initiative with the two big departments that are the Department of Physics and the Department of Engineering, and several institutes that are located in different places in Italy. For example, the National Institute of Optics that is located in Florence, or the Institute of Photonics and Nanotechnology that is located mostly in Milan.
Sorry,
Yes.
ENF is outside CNS.
Yes, so it's different.
Independent.
Yeah, exactly. It's different. So you have two different president and board and so on and so forth. So how do we work? So the organization is the following. So it's organized. So we have essentially three different committees that run the QATN, so the Joint Lab. So we have the Permanent Liaison Committee where the strategic decisions are taken, and we have a representative from all the different partners, so the INFN, CNR, FBK, and the University of Trento. So those four nominates the directors. At the moment, I am the director. And then we have a management board that is formed by 6 researchers that are responsible of the different work packages. And then we have an industrial advisory board. I will tell more about what they are doing. And so this industrial advisory board is made by a couple of industrialists. So Leonardo is a big company in Italy, so owned by the state, and they are have once it was called Finmeccanica, so they have a lot of activity in the field of the army, in the field of automotive, and so on and so forth. So then we have another big company, Italian big company, that is Thales Alenia Space, because as you know, quantum technology is very relevant also for space application. And then we have the CEO of Pascal, that is a French company that at the moment is one of the few European companies that are producing computers, a quantum computer. So this company is located in France. And then we have a representative of a venture fund, so a financial companies that are investing deeply in deep tech startup. So this is Venture Factory. So the idea is to have in the industrial advisory board both industrialists, a representative of a successful startup, and then a representative of the financial market. So what the governance, so what those bodies are doing. So essentially, we have a monthly meeting. So the next one will be next week. And the idea is to try to, on one side, to coordinate the efforts that QATN is playing in the different European as well as national initiative. Just to give you an example, so last year, so there was a call for a national-wide consortia, and within the React Europe framework. So you know that Italy has got a huge amount of money by Europe in order to recover from the COVID, and the national government decided to promote a call for some Italian-wise initiative in specific area. One of these areas was quantum science and technology. And so we, as a QATN, enter into a competitive programs, consortia, and at the end, one of the two was selected, and therefore, so now we are part of this initiative. So the budget of the initiative is something like 200 million euros. So it's really a huge initiative. It lasts for 3 years. There is a huge investment in personnel. And so we are in this initiative that is coordinated by University of Camerino. So it is in central Italy. And so we are with our partner, FBK, NEFN, and CNR. What else? And then, so what we are doing as governance, so we are trying to promote within the community, within these 4 partners, the participation in European projects in a way as much as you are doing here. So we are trying to stimulate people to enter in those European projects. And then
Pathfinder is for the next call.
This one is the last one, so that the deadline, yes, this one was in March this year. And then what we are doing is that we are promoting as the governance contacts with companies and a specific initiative devoted to companies. So we signed this memorandum of understanding with those 2 big companies, and we are trying to formalize also the collaboration with other companies like these 3-1. So what are the pillars of our activity? So essentially what we are doing is that we are working in 3 different areas: research, education, and innovation. As far as research is concerned, so we are essentially covering all the different topics in quantum science and technology because of the participation of all those different departments. So we have physicists, we have chemistry, we have biologists, we have electrical engineering, we have computer scientists. And so we try really to stimulate the interdisciplinary collaboration on those different topics. Then what we are doing also is that not only develop basic science, but also technology. And therefore, we have facility as well expertise in the different platforms on which quantum technology is implemented, meaning the photonic platform, the radio frequency platform, the ion, single ion implantation or single defect center platform in solid state physics, the superconductor platform, and the ultra cold atoms. So we have groups that are working on those different platforms. And specifically also we leverage on the quantum fab that exists at the Bruno Kessler Foundation, where we have the possibility to fully process a CMOS circuit. So we have the possibility to really make devices and to integrate in these devices all the different aspects of heterogeneous integration, like, for example, so we have nanolithography, nanoimplantation, or single ion implantation, or superconductor technology, and so on and so forth. So the way we work is both from a top-down approach. I already said what the governance is doing, but as well as from a bottom-up approach. So the idea is to try really to consolidate the research network and especially the interdisciplinary effort. And so what we do each year, so we call for projects, and those projects are about PhD projects.
It's PhD, not postdoc.
It's PhD, yes. A quantum computing project and quantum technology platform projects. So here the idea is the following. So a specific requirement in the call is the fact that we need to have at least 2 proponents, 2 PIs that are coming from different institutions, meaning that I cannot collaborate. I mean, I cannot get the support by QATN if my project is shared with someone that is coming from my same department. So I need to collaborate between a department of physics and the department of computer science, the department of mathematics with the CNR located in Milano, the INFN Institute in Rome with the Bruno Kessler Foundation in Trento, and so on and so forth. And this is our specific goal in this bottom-up or in this call, is to give not a huge amount of money, but seed money in order to start collaboration, and then to let the people to develop preliminary results in such a way that then they can apply for larger funds from Italy or from Europe.
And you have your internal resources financial for this.
We do have internal resource finances, and then the way we select the project is we use always external referees. So, the management board essentially what does is collect all the proposals, send the proposal for external referees, and then make a synthesis of the evaluation from the external referees. And this is very important because, as we were talking yesterday, since we are locally involved, so it's going to be difficult to say you get the funds and you do not get the fund on the basis of research evaluation, because then people can say, yeah, but your evaluation is biased by a personal relationship. Instead, in this way, so we try on one side to get an objective evaluation of the project, but on the other side also to invest in strategic directions. So maybe, so what I mean is the following. So if two projects get the same evaluation, so then the choice is based on a strategic decision by the management board. Good. So education. So this is also a very important initiative that we are promoting. So I will tell you about more the PhD and the master, but what is also very important from the point of view of promotion of the technology at the local and also national-wise level is what we are calling here lifelong learning. So we get a lot of requests by people working in the company that are about what is quantum science and technologies, what does quantum computing means, what quantum security is worth for our company, and so on and so forth. And so what we are doing is that we are trying also to organize a workshop or meetings with high-level people in companies just to tell them what quantum is, okay? And this is very important. So education, so as I was saying, yes.
I wanted to ask about prototyping and innovation, what it means.
I will come.
Okay.
Okay, I will show you an example if I do have time. Yes. So this I already say lifelong learning. So try to train professionals from companies to follow QAT, the quantum technology evolution. So this is very important. So companies are prone to pay a lot of money in order to get this information. For example, a company with whom we are working is Generali. Generali is an assurance company in Italy, so they sell assurance. But what they are interested in, or for example, Intesa Sanpaolo, that is a huge bank in Italy, and they are interested to see whether by using a quantum computer, this enables them to manage the client portfolio. I mean, and for them, this is really critical issue. So if they are able to speed up the prediction in the evolution of the market faster than the competitors, for them is a real advantages. And so they want to know whether quantum computing and how they can use quantum computing for that specific application. And they are ready to pay for courses, dedicated courses, few of them people, dedicated courses, so they can pay 50 or 100 euro, 1,000 euro without problem. Sorry?
To company.
Yes, yes. No, the companies can.
The company you are inviting to.
Exactly. So
the company.
So the model is.
They're always busy.
No. The model is the following. So we do a weekend, so 3 days in a mountains at. So they can, so they pay 15,000 euro each, 5 people, dedicated courses, and they are really prone to do that. So the master. So this is also a very important initiative in order to, as I was saying before, in order to break the border between the different disciplines and try to have people in quantum at Trento that works together. So since we are universities, teaching is really relevant. On the other side, so there is a huge demand by companies to have engineers, to have professionals formed in the topic of quantum engineering. And so here is, so we are building up, so we have not yet this master in quantum engineering, so the project has still to be approved. But anyway, so here the idea is to make a program that is able to form the professional of quantum science and technology, which can find right now an occupation because they will be highly skilled in problem solving and innovation management. And here, this is a really inter-department effort where all the different departments at the university join a force in order to form people in quantum computing, quantum communication, quantum sensing, and technology. So this is a 2 years long master in quantum engineering. So then the other initiative that we are promoting is a transdisciplinary program of PhD. And here, as before, so we are not doing a new PhD school, but we are essentially proposing an umbrella on which the different students that are enrolled in the different PhD schools find themselves a way to improve their skills in quantum science and technology. So here, as before, so the idea is to break the border between discipline and try to really to promote a PhD student that has both competence in his core, in what is in English typically in the Anglo-Saxon world, they say the major, so in the major topics and in the minor topics. For example, we have a PhD student in physics that is doing a minor with an electronics engineering PhD school. And also in this case, we need to have 2 tutors, one from the PhD school in which the student is enrolled, and the second one from another PhD school. And this is quite successful. So at the end, the student will get a PhD degree in physics with an expertise degree in quantum science and technology. So it's something more for them. Innovation. So innovation, what do we mean? So innovation, essentially what we do mean is the technology transfer of research to the industries. And in order to do that, what we are offering to companies is the possibility to make prototype, as well as the possibility to test their devices. I will be more specific here. Before, I want to give you a few numbers of what we got. So we have more or less 70 research that are involved in the lab. We have formed 35 PhD students in the last years. So we have been able to attract the 1-year C researcher. So this is the amount of funds that before last year we got. So this year is much more because of this huge investment at the national level. And we are also doing and promoting PhD workshop and school. So just in 2022, by this internal call, so we are supporting 6 new PhD students. So we are supporting 3 projects in quantum computing calculation. So here what we are doing is that we are essentially paying time on quantum computers. And so here we are supporting 3 projects that are essentially aimed at make devices by using the technological platforms that we were saying before. So we organize workshop and school, and then this is the kind of support that we receive by the local government in order to finance all those different activities. So how do we work with the companies? So first of all, we convince the company that they get an added value collaborating with us. And the reason is simple, because we are able to cover the whole value chain from fundamental ideas to the possibility to realize a product. I will show you an example if I have time. Then we have expertise that run from software and algorithm to fabrication and testing. So really a broad scope of expertise. And then we have, and this is really important also for companies, so we have a good blend between experienced researchers as well as enthusiastic young scientists that can be then a personal for the company itself. And we are coming from a very diversified background. And so what we propose the companies to do is that the first option is to sponsor one PhD on a subject of his interest. And we have two different schemes. One is a fellowship within a standard PhD school. What I mean is that the PhD student is doing his research within one of the lab of QATN. The second one is a fellowship within, this is a novelty in Italy, what is called industrial PhD school, meaning that in this case, the PhD student is not doing the research in a lab of the QATN, but is doing the research in the company itself, followed by people from scientists from QATN. So they have two options. It's not expensive, so this is the typical amount that they have to pay in order to provide a fellowship. So this is the salary of the students for 3 years long PhD program, so 70 kilo euros. And what else? And then they have to form a formal agreement with a school, because even though the research is done in the company, so the student should have the possibility to publish the result. A second way that we use to get involved with the company is to sign a general memorandum of understanding, which allow on one side to specify what is the field of interest of the company and the way we do run and manage the memorandum of understanding. So typically the way we do run the memorandum of understanding is to charge to scientists from QATN and to representative of the company to manage the collaboration in such a way that they have to report to the permanent liaison committee of QATN each 6 months on the activity they are promoting. Then in the general memorandum of understanding, so we do regulate the intellectual property right, as well as the way we do share the results. And then we do open the possibility to have specific protocols on specific projects on which we do regulate the share of resource. So who's going to pay for the activity, as well as the personnel that is involved in the collaboration. So this general memorandum of understanding is signed at a very high level. So the CEO of the company, as well as the president or the rector of the university, while those specific protocols are managed by the management board. So then another way we have to get a company involved in the initiative is to get them on board on the industrial advisory board. And the scope of the industrial advisory board is to advise the QATN on different technologies, opportunities for development projects. For example, so we get by the person coming from the financial world, that the fact that insurance companies are very interested in quantum computation, and therefore, so he was instrumental in getting a contact with the insurance companies, as well as we asked to the advisory board to help us in define strategies and the way to develop the activity, and especially the transfer of innovation. And then people from company, they do contribute to the strategic individuation of the best direction to which we have to direct the laboratory. And finally, they can advocate for QATN with investor, other companies, or public bodies. So this is very important because that is also a way to prove to the local government that indeed what we are doing is not purely science, which is good doing purely science, but also innovation in terms of involvement of companies. So then a specific instrument that Italy has launched this year, so sorry, is it in Italian, is what is called Agreement for Innovation. So here in this framework, so essentially Italy is putting a few millions of euros to finance a project where a company, together with research centers, is try to promote a specific technology. And so what we are doing is that we are trying to make proposals in answer to this call within companies, and the potential arguments are about quantum security, quantum optimization algorithms. So here we have a project on quantum optimization algorithm with Almaviva, that is a service company in Italy, machine learning, imaging, and sensing. Before to conclude, I would like simply to show you one, maybe two examples. One example of the kind of activity that we perform within QATN and the way that we are trying to use in order to promote innovation. So this is about security, quindi quantum security. So the motivation is, for example, can be seen here. So if you go to this website, you see the number of cyber attacks per second. So here it was a specific day. So that day, so there was something like 500,000 attacks. Here is an example. So it's quite funny to look. So this is an example. This was an attack that was launched by Philippines against something in Portugal, or another one was from. So this is Algeria to Colombia and so on. So one from probably here is Ukraine to US and so on and so forth. So this is a real issue. So the people are trying to steal your data. And so in order to protect the data, so typically what you do is that you are trying to secure the data in such a way by using a cryptographic key in such a way that no one is able to understand or to intercept your communication. So the typical way is that so you have a transmitter, so which is called point A, so Alice, that is sending a message to point B, so Bob. And the way to avoid that an interceptor, an eavesdropper can detect your signal is to use a key with which you encrypt your data, so that when you transmit your data, if has not the key, so you cannot understand what you are sending. So this is cryptography, standard cryptography. And so the way that you assure your security is to have a strong random key. So the probability that the eavesdropper or the attacker can guess your key is extremely low. And so typically those security, so the way you make the random key is essentially based on mathematical algorithms. And so, for example, prime numbers multiplication. So here the idea is that the more difficult is the algorithm, the better ensured is your security. Okay, and so essentially your security is based on computational power of the adversary. So the problem is the fact that at the end of last century, so Professor Shaw demonstrated an algorithm by which he was able to prove that if you have a quantum computer, then it's extremely easy to break all those cryptographic techniques. And so people say, oh, that this is a real threat to security because of quantum computing. And so people start to say the cryptography apocalypse. So when a quantum computer will be here, so everything will be broken. So the security will be broken. So the US make a study that was about how to address the national security risk because of the emergence of quantum computing. And so here is really a big threat, a big issue. And so people is saying, so since it's the quantum computing, the threat, so why don't we use quantum physics in order to ensure the security? And so this is the topic of quantum cryptography. And so in quantum cryptography, you are not, so the security is not, or the protocol is not based on a mathematical algorithm, but is based on quantum mechanics. So I can give you an example. So in order to produce random numbers by using quantum mechanics, so it's very easy. So what you do is that essentially you take a beam splitter, you take a photon, and then you shine with this photon the beam splitter. And then you know that quite accurately the physics of this problem. So you know, so you are able to really very well describe the physics of the problem. And at the end, it turns out that your photon has the 50% of probability to go here, to be transmitted or to be reflected. And you know exactly the physics of the problem. Okay. And so the photon, since you have a single photon, so then you will have 50% of the probability, but actually what happens is that sometimes the photon is going here and sometimes the photon is going there. And therefore, when the photon is here, you click 1. When the photon is there, you click at 0. And so you have a random number generator whose security is proved by quantum mechanics. Is this experiment different from the tossing of a coin? Yes. Because the tossing of a coin is a deterministic, so it's a classical physics problem. And in classical physics, as you well know, Newton's law say that if you know exactly the initial conditions, so you can predict exactly the evolution of your system. In quantum mechanics, this is not true, meaning that if you know exactly what is happening, you can only probabilistic say the outcome of a measurement. In classical physics, not. And indeed, so there was this famous case of the Pelagios, that is a family in Spain that by observation was able to break the casino, the roulette in the casino. Also, they became millionaires without doing anything else than describe correctly what is happening in a roulette. So quantum physics is extremely different than classical physics. And so this example here is strongly different from that example there. So no statistical model is assumed, as in the tossing of a coin. Everything is known by everyone. Despite this, the result of the measurement are random. And so what people now is doing is that try to use quantum mechanics in order to promote a quantum cryptography. And this is a huge market. So this is the forecast in the growth of the market. And you see that in the next 5 years, the quantum cryptography market will grow by 30%. So this is the number of dollars that the revenues in QRNG, so quantum random number generator, that is predicted to grow exponentially, and in 5 years, no, at the end of 2020, so they say that you have a market that is worth $3 billion. So a significant market. So this is the market of quantum cryptography. And so what we said, here there is an option, an opportunity for making something new that where we can say something. And so what we try to do is that we say, okay, why don't we produce a random number generator based on quantum physics that is cheap, compact, and compatible with CMOS, in order that you can put in any of your portable devices. And so since at that time, so this is a few years ago, we were working on LEDs based on silicon nanocrystals. So what we were thinking was, since spontaneous emission is a probabilistic phenomenon, so you excite. This is what happens in a light emitting diode. So you excite an electron, and then this electron relax after some times, and sometimes it emits a photon. So you cannot say when the photon is going to be emitted. You can also say that in average, you have an emission of a photon after a radiative lifetime of the electrons. But you cannot say whether it is in the first nanosecond or after 50 nanoseconds. And therefore, now, if you have a single photon detector, so this is the capacity of FBK to make those single photon detectors, so that by simply counting, by simply measuring the arrival time of your photon on the detector, so you have a source of randomness. And so you can make a quantum random number generator. And so we say, okay, this is great. So let us try to first prove that this is valid. So we have this wafer where we have our LEDs. Here we have a single photon avalanche diode, so the single photon counter. Then we have a fiber. So the wafer is emitting photons. We are counting, and indeed, so we prove that this is a quantum random number generator. And so then we try to decrease the size. So we package the nanocrystal on top of a silicon photomultiplier. Then we bonded together the two chips. And finally, we do integrate everything within a very small microelectronic device. So this is the cross-section of the device. So everything is extremely small. So you have the LEDs here, you have the photodetector, and then you have the logic that process the signal. And so everything was squeezed within the small microelectronic circuits. We were very proud, but unfortunately, at the very same time, another company in Geneva that is called ID Quantique put on the market these very same QRNG chips. And so we say, oh, what can we do more than what they are doing? And so this came the opportunity done by collaborating with other departments, and especially in this case, so we were collaborating with the mathematical department where colleagues were studying about the foundation of quantum mechanics. And so what we asked them was, if you have a system, how can you prove that your system is really quantum? Because in that case, if we can prove that the system is really quantum, so then we have an advantage with respect to the other, because our is quantum proof. And so we go back. So these people were working on foundation of quantum mechanics, and they say that this is quite simple, because even at the beginning of quantum mechanics, so there was this debate by Schrödinger, Einstein, Planck, and so on and so forth, that were saying, what is entanglement? And so Schrödinger said that if you want to prove that something is quantum, so you have to prove that show entanglement. And you know this debate, and the debate ends up with a Nobel Prize last year to Aspe, Closer, and Zellinger, that actually they demonstrate the possibility to have entangled photons, and entangled photons violate the Bell inequalities, and therefore the only explanation of nature is quantum mechanics, or all the theory based on hidden variables that are the theory that Einstein was promoting. All those theories are not valid. And so the idea is that, so if you want to prove that you have a system that is purely quantum, so you have to use entanglement. And so then people came and say, okay, so we can use entanglement in order to exchange a key in a secure way. And the way that they use is that they use entangled photons, and they send those two entangled photons to two receivers, so to Alice and Bob. And since they are entangled, Alice knows that if she measures a polarization state, the other photon has the opposite polarization state. And therefore, by doing the measurements on those photons, the other photon collapse on this other state. And therefore, you have the two sequence of random bits, and you are exchanging those two sequence of random bits. And therefore, you have a key for Alice and a key for Bob. They have the same key, and so they can encrypt and decrypt the message without problem. And so this is the technology of QKD, quantum key distribution. And so this is also the Nobel Prize motivation for Dellinger that actually used entangled photons for a series of quantum information application. And so what we say that, so this is what the other are doing. So why don't we try to do something else? And so we try to use this different source of entanglement that is called single particle entanglement. So the one I showed you before is an entanglement between two different particles. Here we are using the entanglement within the single particle, meaning that what we are doing here, we are entangled together two different states of the same particle. And what we are using is the momentum degree of freedom and the polarization degree of freedom. And therefore, what we are binding up is an entangled state where you have the entanglement between a photon that has a given degree of freedom and the degree of freedom and another degree of freedom. So this is a momentum state and a polarization state, or superposed with the same photon that is found in another momentum state and in another polarization state. And so this is an entangled Bell states that violate the Bell inequality. And so the problem is, how can we build up these entangled states? And so the idea is very simple. So you take a photon, you fix the polarization state of the photon, you fix the direction, and so now you have this initial state for your photon. So 0 is going in that direction, and V has vertical polarization. Then you use a beam splitter. And by using a beam splitter, now you create your superposition state between the photon that is going through and the photon that is going up, the photon that is transmitted and the photon that is reflected. And so this is now is the wave function that describes your photon that is in a superposition momentum state and in a given defined polarization state. And then you add a polarization rotator. And now you have the generation of an entangled single photon state, because now you have a superposition between a photon that is here that has the 0 momentum degree of freedom and the horizontal polarization state that is superposed with the photon that is with the same photon that is here that has a different momentum state and a different polarization. And now you have your resource in order to prove that indeed by using this single particle entanglement, so you can violate the Bell inequality. And now if you are able to demonstrate the violation of the Bell inequality, it means that what you are observing is indeed a quantum phenomenon. And then you can build up an experimental setup where you generate your entangled single particle states, and then you are projecting those entangled states on the basis that is momentum and polarization base, momentum and polarization base, momentum and polarization base, and so on and so forth. And then you can build up your quantum random number generator, because at the end, when you do the measurements, you can have either a photon here or a photon there, a photon here or a photon there. And therefore, you have your random numbers that are generated by detecting all those clicks. What is different with respect to what all the others are doing? So the difference is here, that we did the test by using a laser as a source of a single particle entangled state, but as well as an LEDs. And so what here is different dramatically with respect to all the other approaches is that our light source is not a laser, it's an LED. And so what are the differences? Is the fact that LED is a cheap device, is a low power device. And so what we are now able to do is that we are able to implement a QKD, so a quantum key distribution scheme, by using an LED instead of a high power, expensive, power angry laser. And so we can use a single photon instead of 2 photons. So this makes much more easy the measurements. And therefore, so we can make a QKD system that is simpler, cheaper, lighter, consume less power, and since it's based on entanglement, is even more secure. So we integrated everything on a small chip. So this is the chip where we are producing and distributing this QKD. So the chip is coupled to optical fibers. So here you have optical fibers. So it means that you can distribute your key. And then what we are doing was that we proposed to the university to make a startup that was approved, and with aim to produce this system for quantum key distribution. And so in the startup, so we have photonics scientists, quantum information scientists, and we are trying to produce this system. So what is the product idea? So the idea is to have a very simple compact system that can fit within a memory stick in order to allow a quantum key distribution based on single particle entanglement, and therefore the light source can be a cheap LED instead of a large laser. And our aim is to make a system that is able to be used in local network in order to exchange secure information between 2 different offices. And the target market is the automotive, the Internet of Things, the intra-building or intra-campus communication systems. And what are the typical advantages that we are figuring out with respect to the competitor? So those are many different competitors. So ID Quantique, so this Switzerland company, but you have also other, so this is a British company, you have Toshiba, and so on and so forth. So what they are doing is that they are doing extremely good systems, which are used for long distance communication, so length in the order of 1,000 kilometers. So the size of the device is like a rack device. So this typically is 10 kilograms in weight. And so since you have a lot of high quality photonics inside, so the price of the device is in the order of a few 10,000 euros. Our target is short distance, small size, small weight, and more importantly, small device price. And how can we reach these numbers here is because so we have a system that is dramatically simpler with respect to the other, because we do not need to have 2 photons generation. So we do not need to have a strong laser in order to produce the entanglement and to distribute the key. So the company is going to start in September, and I hope next time to come here with my personal helicopter. That will mean that I will got a lot of money. Okay, so thank you. I think that I can finish here.